In this video, we are going to study another example of a Banach space, and we're going to precisely calculate its dual. The idea would be that we are going to study a simpler Banach space than L infinity. So we still don't know what is the, we haven't discussed in this course the dual of L infinity. It's actually a huge Banach space. But with the following example, we will have a little bit of an idea what how complex is the situation. So the function space that we are going to consider are those functions on a proper metric space that are continuous and tend to 0 when they go to infinity. Okay, I will make precise the definition. So let's E, so it's a set with a distance, so it's a boundedly compact also called proper metric space. I remind you what this means. This means that all closed and bounded sets are compact, or equivalently, one can just require that all closed balls are compact. Means given a point x and a radius r, all those points whose distance is less or equal than r from the point x. Okay, so what do we do now? We consider mu. I recall you this fact that if mu is a measure on the set E with sigma algebra given by the Borel sets, and this measure is finite on compact sets, so in our case finite on balls, it's the same, then what we have is that, okay, mu is sigma finite. This is because exactly, right? If I consider the closed balls of radius n at a given point, this is finite because this is a compact set, and as n goes to infinity, this is an exhaustion of the whole space. 2, I recall you that mu is a regular measure, which means that for all sets in E, then the measure of A is the same of the supremum of all the measure of the compact sets that are inside A, K compact, and also it's equal from the inf of the measure of those open sets that contains A. Okay, so let's keep in mind this property for measures on a boundedly compact metric space. Now, on the space E, it is interesting to consider the compactly supported continuous functions. We already did in the course, continuous functions. Okay, so I recall you the symbol. So is so with C0 on E, I will usually denote the continuous functions. If I put a C at the bottom, this is with compact support. So this is by definition all those functions continuous such that there exists K compact, so subset of E compact, such that F restricted to the complementary of this compact set is constantly equal to 0. Okay, we already considered this space, and for example, when we were discussing the horizon lemma. Okay, and it's easy to see that this space is a vector space. Is a vector space. And now one should naturally ask the question, so is it a Banach space? Of course, to have a Banach space, one should first clarify what is the norm. What is the norm that we are considering? Okay, in this case, since the function is has compact support, then and is continuous, then on this support it emits a maximum. So one can consider this maximum as a norm, because if this maximum is 0, for example, the function is 0, it's the 0 function. So the candidate is for f continuous with compact support, we consider the subnorm to be the maximum of f x in E, or maybe let's call it sup first. But then also we know that in the case these are continuous function with compact support, this is really a maximum. And this is when we see f as so this is a finite number, which also means that we can see these functions as a function in the LP space, and this is nothing else than the L infinity norm. Okay, so in other words, what I'm saying is that we can see C0 compact supported as a subset of L infinity. Okay, L infinity of E. It means all those functions that are bounded. So fixed a norm, a measure, and considering measure, call it mu, and considering the equivalence relation mu almost everywhere equal for functions, we can consider C0 as a subset of L infinity E mu. Okay? And it's important to notice that in this inclusion is still injective, because you see, if you have two continuous functions that coincide almost everywhere, then in particular they coincide on a dense set. And being continuous, this means that they coincide everywhere. Okay, good. So, and therefore, right, so this is a Banach space, and therefore we can see this set as a subset of this Banach space. So on C0C, we consider the induced topology, which is the same thing of saying we restrict the norm from L infinity. Let me rephrase the question that we asked before, whether C0 compactly supported is a Banach space. So I want to remark that now asking whether C0 compactly supported is a Banach space with the subnorm is the same as asking whether it is complete. So now we have the norm and we are asking, is this vector space with this norm is complete? So with respect to this norm. And we know already that L infinity is complete. Right? So if you have a Cauchy sequence, then it converges in L infinity. So now we want to know if also if the limit belongs to this vector space. And therefore, this question is the same as asking whether C0 compactly supported is a closed subset of L infinity. Answer is not. It is not true that this is a closed set. And therefore, it is interesting to study the closure. So let me write some. So C0 compactly supported is not closed within L infinity. What is the closure? Its closure is the following set. Okay, we will call it C0 with a 0 at the bottom, which stands for being vanishing at infinity, being 0 at infinity, going to 0 at infinity. What does it mean, infinity? Infinity is outside a compact set. So, right, let me be rigorous. So this is the definition of a set, and then we will prove that this statement is true. So we consider continuous function with the property that for every epsilon, there exists k in E compact such that if I consider f restricted to the complement of this compact set, it's not 0 necessarily, but its norm, so its absolute value, is less than epsilon, where this compact might depend on epsilon. Okay, so we might call it, so we will say that elements in C00 go to 0 at infinity. Okay, this is just terminology to summarize this definition here. Okay, so let's prove this statement. So I'm going to prove the following theorem. So let's E be a boundedly compact metric space. So the closure within L infinity of C0 compactly supported is equal to C0 vanishing at infinity. So this is the proof that I want to present. Okay. Proof. So both these inclusions are not immediate. Okay, it's not very difficult, but we have to prove that double inclusion. So it's a double inclusion. Okay, let's prove this inclusion first. So take function f in the space on the right. So C0, 0. We have to prove that it's in the closure. So we fix epsilon, and we know that function goes to 0 at infinity, so we can take K, a compact set, such that f restricted to the complement is less than epsilon in norm. Okay, this is by definition of C0. Okay, by Urison lemma, we have that there exists a function h compactly supported such that the norm of h, subnorm, is less than 1. It's going to be 1. And h is greater than the characteristic of k. So remember, the picture was we have some k, and then we have a function that decreases in a neighborhood of k. So it is 1 on k, it goes to 0 continuously, and then outside a neighborhood of k, still bounded, and therefore inside a compact set, is going to be 0. Okay, this is what Urison lemma was constructing. Okay, so now what we do, we consider the function g to be f times h. Okay, so since h has a compact support, then this product, so this is a product of two continuous functions, so the function is continuous and has compact support because h has compact support. All right, so this should be we have to prove this is an approximation of f in the norm of L infinity, and it's an element in here. So let's prove that these functions are closed. So gh minus f, so gx minus fx. So by definition, we said that g was f times h. So this is norm of f of x times we have h of x minus 1. Now, this quantity, so if x is in k, h of x is equal to 1. So this is 0. so we have 0. Instead, if x is not in K, then what we have that, okay, so remember h was a function between 0 and 1. I remove 1 and I get something that is inside -1 and 0. Instead, this other part, we have that on the complement of K, this was less than epsilon, by the way we chose K. And therefore, this absolute value is less than epsilon. So less than epsilon. Okay, good. So what we have the sup norm of this difference f minus g is less than epsilon. Okay. So therefore, what we prove is that the compactly supported functions are dense in the continuous functions going to infinity. Okay, one inclusion has been proved. The other inclusion. So now we take instead f, a function that is in the closure of the compactly supported functions. And now we fix some epsilon. Now, since f is in the closure, we can take g compactly supported functions that is epsilon closed to f in the sup norm, and g is since g is compactly supported, then there exists k compact such that g outside this compact set is constantly equal to 0. Okay, now so we have to prove that f is a continuous function that is going to infinity, it's going to 0 at infinity. Okay, so first of all, let's prove this second part first. So what do we have? That f restricted to the complement of k. So you see, outside of k, g is 0. So I can just write f minus g restricted to the complement. And we know that this number is less than the sup, right? So this is less than g minus f, which is less than epsilon. Okay, so we prove that for any epsilon there is a k, such a compact set, in such a way that outside of this compact set the function is less than epsilon. But now we need to show that f is continuous. Okay, let's fix a point. So check continuity at a point, arbitrary point, x in E. Okay, so we have this x in E. And remember, we already fixed the epsilon. It's already fixed. We know that g is a compactly supported continuous function. So g is continuous at x, and therefore there exists some delta such that if the distance between x and y, so if y is another point at distance less than delta, then the image points have distance less than epsilon by continuity at x. Okay, so now this is what we proved. What do we took the delta. Now what we do now, take y in E such that the distance x and y is less than delta, and we have, now let's consider the distance between f of x and f of y. Now, triangle inequality. Triangle inequality, we can write this as f of x minus g of x plus g of x minus g of y plus g of y minus f of y. Now, the first one is less than the sup norm between of f minus g. Likewise, this is less than the sup norm, and this, by the choice of delta, is less than epsilon. Okay, so what we have, that this number here, this is less than the sup norm. So what we have is that, and this sup norm is less than epsilon by the way we constructed g, pick g, right? So this is 3 epsilon. Epsilon was arbitrary. We proved continuity.